Uh, Great. Okay, so let's start today class. We talk about game theory, the motivations, and the tools, uh, especially probability theory as well as uh, linear programming. So the people at Zoom, do you hear me well?
Yeah.
Good. Okay, so we are continuing this with like we talk about some kind of formulations about the utility function that we can represent utility function as something that the people may have a different preference, but at the end of the day, we can turn everything into numbers essentially, and we can consider the utility function. We talk about normal form games. This is like some kind of formal representations of the game, and lots of game actually can be interpreted as normal form games. That's a very important representation of game that we talk a lot about. And here we want to talk about some important normal form games. We already talked about prisoner dilemma slash uh, like chocolate game, but here we are talking about uh, more about some other ones. And these are important. We are referring to these games a lot, so it is important that you know these games essentially. These are very simple games, but I think these are very important at the end. Good. So good. So the first thing that we want to talk about is the common payoff game. So here, for every action profile that the people will take, and if you remember, action is just the action that one person takes or strategies. And for example, here, this is one action that this guy, the I think column player is doing, and this is some actions that the right player, row player is doing. And action profile always means vector of all actions, actions of all people. So here for all action profile, all agents have the same payoff. So for example, if you see here in this game, this is called which side of the road. And here, if both of them take left, left, they get the same thing. If they get left, right, they get the same thing. So it is essentially pure coordination. And it's a team game because every action that you are taking, everyone gets the same payoff. And here, the idea is that you want to essentially choose an action that uh, maximize the benefits of all, essentially. So you will essentially, you can see in this normal form game, uh, you may try all possibilities and take the one that has the maximum benefit to all. An important game is which side of the road. So there are two people driving toward each other in a country with no traffic rule. So each of these people decide to go left or right. I mean, left of the road or right of the road. And there is no rule, as I mentioned, there is no particular rule here. So they need to essentially coordinate their actions such that there is no accident. So if you, as you see that, I mean, if both of them take left, right side of the road, or both of them take right side of the road, still, both of them should be fine. So there is no accident, they get the maximum benefit. But if one gets left, the other one gets right, and again, left and right of themselves, we are talking about. Or vice versa, then both of them have accident and they get payoff zero. So this is called common payoff games and total coordinations. And if one of them essentially, like for all action profiles, for all vectors of actions, and here we are, note that I mean actions and pure strategies generally are the same essentially here. So for these actions that they are taking, and these are the pure strategies or actions that they will take, they get the same payoff. So that's I mean, which side of the road game and important common payoff games. Let's go. And we are referring to these games a lot later. So and that was actually interesting. So this just something related to this, that this was actually happened in Sweden on September 3, 1967, and I think it is like almost midnight. That they were supposed to go to the left side of the road, everyone, and they changed the route to make it to the right side of the road. And this is at the midnight. I believe it was midnight that the rule changes, and you see the chaos that happens essentially on the streets. So that is which side of the road is really in practice. It is important that even like 1 minute in the middle in the transition can bring lots of chaos essentially. And here, we are talking, as I mentioned, we talk about game theory and in particular mechanism design. I just remind you that in the mechanism design, we want to put the rules such that if people essentially goes according to their incentives, if the people are selfish, then we get the desired outcome that we want. So that's the whole idea of mechanism design. And of course, mechanism design should not cause chaos like this, even in the transitions. So we talk more about mechanism design, especially, for example, for auctions and others later. But this was some, brief things about or reminder about mechanism design. Another games that we are talking, these are somehow completely the reverse of common payoff games are zero-sum games. So these are purely competitive. The other one was purely somehow collaborative. This is, or teamwork. This is purely competitive. So here we know that for every action profile, the sum of the payoff is the same. So in the previous case, we knew that the actual payoff were the same. But here we know that the sum of the payoffs is the same. So essentially, it means that if I play a game with you and you win, it means that I lose, or if I win, it means that you lose. And what is more formal is that there is a constant C such that for every action profile, so this is action profile, this is a vector of the actions that the people are taking. The utility of the first person plus utility of the second plus utility of the nth person is equal to C. So this actually it is called constant sum games, but we already discussed about the transformations, or especially affine transformations, that we can do it for the utility function and get the same thing. So in some sense, as long as we keep the monotonicity, it's the same. So here, if it is some C, so if some of the utilities for every action profile is C, we can just simply subtract Cn for every payoff. So essentially, we take the coefficient 1 and we just decrease essentially Cn from everything. So then some of the all utilities would be just 0. And that's the one that we talk. So this is the reason that when we talk about constant sum games and zero-sum games, these are the same games under this affine transformation, positive affine transformation that we talked before. So we talk about utility functions, and we mentioned that, okay, the preferences can be turned into utilities. And the utilities also somehow, the game remains the same as long as there is some affine transformation. And this is here's a good example that the constant sum games become zero-sum games because of this affine transformation. So if you say constant sum game or zero-sum game, they are the same. Still, the people use both terms, but they mean the same thing. So there are, again, some famous games that are zero-sum games. So matching pennies. What is the matching pennies game? So here there are two agents. Each of them have a penny. each independently chooses to display head or tail. If it is the same, agent 1 gets both pennies, and otherwise agent 2 gets both pennies. So you can actually represent the normal form matrix as like this. So this is the heads and tail and heads and tail. So the first player, if both of them are heads, the first person wins. Why wins one? Because he already had 1 penny, get 1 more penny. The other guy loses 1 penny, so it would be 1 minus. So if it is tails versus head, then this guy essentially loses its penny or her penny, and the other person gets 1. The same thing here also, I mean, if heads and tails, and again, tails and tails. So this is a pure competitive game, matching pennies. Because in some sense, your loss would be my win, and my win would be your loss. Or my loss would be your win. Another one is the, I mean, penalty kicks in the soccer. So there is a kicker and a goalie. Kicker can kick left or right, and goalie can jump to the left or right. So kicker scores if he or she kicks to the side that the goalie is not there. And you can write the same thing that here, for example, this is for this guy, this is the kicker, for example, left, right, and the other guy, left, right for the goalie. So this is kicker, and this is goalie. So if both of them essentially is left, left, then in this case, goalie wins, and this guy loses. And if right, left, then this guy wins, kicker, the other one loses. And if this is this one, also 1 minus 1, and the other one would be minus 1. So that's another one that, and as you see that, again, some of these guys, for all of them are equal to 0. That's the thing, that is a constant sum game. Good. And it would be interesting and important to think about other games. So you may, as I mentioned, the whole life, you can consider it as games. So it would be interesting to see where are the places that you will see constant sum games, and where are the places that you are seeing, for example, common payoff games. And or like somehow in between. Sometimes essentially it's not constant sum games. Like what are the in-between case? The in-between case is that there might be some case that like the sum overall action profiles essentially are not the same. So it means that sometimes coordination pays off, sometimes competition pays off. That might be, I cannot say actually the more practical way. Lots of the time, actually, the games that we are doing is zero-sum games. Not all the times, but lots of them, I mean, you will think about it. You are negotiating something with a bank. You want to essentially buy a house. Almost all of them essentially is this type of competitive games that your loss would be the win of the other person, and your win would be the loss of that. So these are the zero-sum games are indeed very practical games and very important games. So again, there are some cases that might be not completely zero-sum. For example, a case that is in between would be that like 2 countries negotiate essentially to stop the war. So in that case, I mean, both of them, okay, they don't completely win or get the things that they have it, but if they coordinate to stop it, then they get some benefit out of it.
I think that one is going to Christian's dilemma. Right?
What was that?
I think that one would be similar to Christian's dilemma. They both stop the war, then they both get benefit. If one of them stops it, it doesn't, then Well, one of them gains everything from the other one, and they either of them stop it or get a huge loss.
Exactly. So that is like, as you mentioned, like President dilemma is one very good example of that. So these are, in some sense, these are the ones that we are talking, and these are like the practical ones that the people may use essentially in life, and you should use them because you can understand the world somehow better. So which of these scenarios are that? So these examples are really important to, such that when you see in real world different essentially uh, games, you can see which one, this one is similar to which of these games that we have. Another one that you have heard about, again, the very famous one, but there are lots of course, zero-sum games, but this is another one, rock, paper, scissors. I mean, this is with three actions. That's the thing that we are talking. So, I mean, probably all of you know that. So these are like two players. Each of them brings rock, paper, or scissor, and rock beats scissor, scissors beats paper, and paper beats rock. So this is essentially the matrix that we can do it. And this is important. You see, sometimes when we want to represent this normal form game, we can represent them like this. And in the normal form game, we are just representing both payoffs in one essentially place. But you can actually, sometimes we are not doing that and we are having a separate matrix for the first player and for the second player. So here you can actually have it. And this view also is important because for some other games, actually just giving one of these matrices for symmetric games, if we just give one of these matrices is enough. We don't need to do it for different people. And we talk about them. So here we have two matrices, R1 and R2. And again, rock, paper, scissors, rock, paper, scissors. And if it is rock, rock essentially means tie. And paper, rock means one essentially. And scissor rock would be -1. Anyhow, these are like the this essentially the concept of bits here is represented in this case for these two people. And this is another way that we can actually represent these games. So, and again, here means that if this guy brings paper, the other guy brings rock, then the first person essentially wins and the second person loses. So that's another famous game, which is a zero-sum game. So of course, as we discussed, I mean, there are some places that we have non-zero-sum games. So a game is a non-constant sum or non-zero-sum if there are two action profiles for them, the sum of the utilities are not the same. Of course, a prisoner's dilemma, as you mentioned, is a very good example of this. Here, the sum is equal to, so here the sum is equal to 6, while the sum here is equal to 5, while the sum here is equal to 2. So for different action profiles, we may have a different sum essentially. Another one, it is again, these are some of the history for some of these games. And it is important to know that. And the people, there is some tournaments of these games essentially in the repeated games and others in the AI community, they will consider it. So these are not just some particular games. They really try to formulate some situations in the real world. As you mentioned, for example, when we talk about the war situation, you may think about prisoner's dilemma or other things. So these are really famous things that you need to think about it. And maybe the first time that I have seen, I think back in maybe 2000, 2001, that I was in some conference and the people were talking about this. Actually, it was an invited talk. So okay, so why do people consider this? But like now, I will think completely differently, because these are the things that you will see something in the life. You say, oh, this is actually prisoner's dilemma. And then we will talk about equilibrium concept and solution concepts. So in that case, oh, this is the game, so this is the equilibrium and we should do that. Or what will happen if we are playing this in a long run, the repeated game, what should we do? So these are really important games, essentially, that we consider it. So what is the battle of sexes? This is the good. So good. Here there are two agents. They need to somehow, there is some kind of coordination, as I mentioned. There is some coordination versus some competitions. So there are two agents that they need to, coordinate their actions, but still they have different preferences. So the original scenario that was mentioned for this game is that husband and wife. Again, this is like a thing, as I mentioned. Everything in life essentially is a game. Husband and wife. Husband prefers to go to football. Wife prefers to go to opera. Now, this is another thing that you can mention. Essentially, two nations that they need to work together to have some international crisis such that they can put an end to it. The same thing. The different scenarios might be, some scenarios might be more preferable for others, but if there is no coordination, then they get zero. So here in this case, so if the wife and husband, if they and each of these persons decide individually want to go opera or to football, but and this is they want simultaneously they decide. So if both they go to opera, then wife gets a better preference too, but husband is not unhappy as well. Will be together, so it will be 2-1. But if one goes to opera, the other one goes to football, then both of them get zero essentially. So they prefer to be together. That is, but they don't want to be essentially alone. But at the same time, each of them have different preferences. If they go to football like wife goes to football and husband go to opera, then it would be 0-0. And if they both go to football, wife gets 1 while the husband gets 2. So this is another one that is like a good example of non-zero sum games. Good. Another games which are very important are symmetric games. So in the symmetric game, every agent has the same action and the same payoff. Like a better definition is this: if we change the role of the player 1 and player 2, or maybe more than two players, then the payoff matrix remains the same. So it means that if you have even 3 players, you don't need to say this is the row player, column player, I don't know, the third player. You can put them arbitrarily and still the matrix remains the same. So in some sense, the player in this case, they don't need to have a label. You can change their label and still the payoff will be the same. So let's see an example. So for example, if you consider which side of the road. So here, you don't need to actually, you can just say always this is, so this is, in some sense, you don't need to have all of these things. You can say this is the first player, or this is the first or second. And this is the other player. So it can be first or second. So you can see that if the first player is doing left and the other player is left, it gets 1. And it is independent whether it is the first player or second player. And in particular, in the 2x2 symmetric game, doesn't matter that this agent one is the row player or the column player. So for two people, the common payoff matrix looks like this. So, this is if this is a two-player game, and each of them have two actions, then it would be something like this. That if we don't say that which player and we don't say which action, so the actions are the same: A1, A2, A1 and A2. And here say that if A1 and both of them take the A1, A1, then get W and W. And if A2, A1, it would be YX, and so on and so forth. So that would be a typical form of it. And as I mentioned, so you can actually have a more compressed representation, because you can always consider you don't need to essentially show both payoffs here. So you can say this is the first player. So you can say you can consider a player here versus the other player. So in that case, it doesn't matter this is the first player or second player. We can always essentially consider this one. So you say that like if this is the first player or second player, take A1, A2 versus the other player gets A1, A2. Still, these are the things that you can do it. And you can see, for example, here, if we have the first player here, second player here, or we have the second player here and first player here, still it would be the same matrix. That's essentially that's the whole thing. So we don't change the matrix. And you can also generalize this is more than two players. So you can always think that, there's one player versus how many people. Essentially, you don't care that who is doing this, how many people take these actions, how many people take these actions, then that would be the payoff for these guys. Again, so there is no label here. We more talk about the symmetric games when there are two-player games, but you can define it for more than two players as well. And the people will consider that one as well, that you don't care essentially who is the person that is doing that. Good. Now that we have defined these games, let's go a bit more formula. So here we are using pure strategies. Pure strategies are the same as actions. So when here we consider essentially the normal form games. So each of these guys, they will take A1, A2, A3, and so on and so forth. This guy A prime 1, A prime n. And as we discussed, if this is a symmetric game, it would be the same essentially actions. But these are actions. At the same time, these are pure strategies. So, okay, so this is the question that when we talk about pure strategies versus what? Pure strategies versus mixed strategies. Mixed strategies means randomized. And that's the one that we are talking a lot. That's the main reason that I mentioned I cannot teach this course if we don't know probabilities, or if we don't have a common grounds about probabilities and probability theory. So here, a mixed strategy is something which is randomized over a set of actions. More formally, you have this is the strategy of player I. So SI generally, as we discussed, it means that a strategy of player I. So SI means, and we have again a strategy profile. When we have S1, S2, to Sn, this is the strategies of these people that they have. Now, Sj of Aj means probability that action Aj will be played in a mixed strategy Si. Good. What is the intuition for mixed strategies? Of course, the people may do random, essentially, things that like I play versus you do some kind of random way. But this is not just a random way. You can think about also the history, for example. You may say that two people are playing with each other, and this is the history of it. This is a game that, for example, they are doing a lot for at the soccer games. They are considering these are some strategies that they are considering this team that how did it play before, or like for example this goalie, if it goes to the penalty kicks, that this goalie, what was the overall history of this person that went left or right, and also both for a goalie and for the kicker. So that's something which happens, lots of cases. As I mentioned, a good example is the soccer game, that there are such kind of analysis, and the people actually do the analysis and exactly get these probabilities. And when goalie, especially when go to the penalty kicks, then this history that and in the soccer especially is very important. If unless the kicker already sent the ball to the out or outside of the goal, if it goes to the goal, then it is very important whether you go to the correct one or not. And this is an example that probability actually turns into or history turns into probability. That's one idea. The other idea, behind our motivation for this is that, you don't know the other agent. If you don't know the other agents, you may put some probabilities essentially there. Or you don't know all the motivations of the second person. You can just, at the end of the day, you can just put some probability that you are doing this or that, essentially. That's the idea that we talk about the mixed strategies. And it is actually also very practical thing, especially because of the history, because it is not the case that we know these guys are just taking this action or this action. It can happen that they are taking some randomized thing between systems. So the support of SI, again, also you can think about this one. So SI actually is a distribution over actions. So in the mixed strategy, it is SI is a mixed is a distributions over all possible actions. The support of SI would be actions that have probability greater than 0 in SI. This is like a support of any distribution that we define. So a pure strategy is indeed a special case of mixed strategy that puts all the probability on just one action. So in that case, the support of the pure strategy, or a strategy which is pure, has only one action. It would be fully mixed. It would be the reverse, that the probability of all actions are greater than. So in that case, essentially, the support is the set of all possible actions. And as we discuss again, so the same thing that we talk about action profiles. So action profiles, the actions of each of them. And action profiles, you can think about more like a pure strategy profile, that each person takes one action. But here we have more generally a strategy profile, which is an n tuple S1 to Sn of strategies, one for each agent. And each of them, S1, S2, and Sn, by itself can be a mixed strategy. So itself is a vector in some sense. So we have vectors of vectors in some sense. That's the way that you need to think about it. Okay, so this is actually, let me use this other. These formulas are better, I think. What's this one? This one. Stop share. So, let me this. Give me 1 second. Good. So expected utility. Uh, so when we talk about pure strategies, here we are in the pure strategies, we are like when we talk about normal form games and the matrix, the payoff matrix, it only talks about pure, essentially about pure strategy profiles and the payoff for them. The question is that what about for mixed strategies? How can we get the utilities? And that's again the part that the joint distributions become very important, the one that we discussed before. So when we want to, for mixed strategies, we cannot say just what is the payoff. We say what is the expected payoff. Because when we talk about randomized cases, we can only talk about expectations and not just a pure number. So, like, let me give you an example. Good. And the people at Zoom, you are seeing my drawing, correct?
Yeah, we can see it.
Yeah, good. Okay, so you see we have the action 1, action 2, action, I don't know, 4 here, A4. And this is B1, B2. So this is this guy, for example, S1 and S2. These are the player 1 and player 2. And this is a strategy of player 1, and this is a strategy of player. And both of them are mixed. What's the meaning of that they are mixed? It means that, so there is some probability. So here, P1, P2 to P4 here. And here also say I will call it Q1, Q2 to Q4. So these are the probabilities. What's the meaning of the probabilities? It means that some of the Qi's are equal to 1 and some of the Pi's is equal to. So this is the probability distribution, as I mentioned. Each strategy is a probability distribution over the set of actions. And these are, we are talking about the discrete case. And of course, all Qi's are greater than 0, and all Pi's are greater than or equal to 0. And here, we will consider a joint distribution of these people. And we are assuming that these two guys are doing it independently because this is a simultaneous game. So you don't know what are the actions of the other persons. So each of them are doing in a simultaneous way. So in that case, what is the, because it's an independent case, what is the probability that this person is doing B1 versus the other person is doing A1? It would be P1. So for this guy, would be P1 times Q1. So in some sense, it is exactly the joint distribution that I have mentioned. And here we are considering independent. So it means that in each of these cells, we will be, so it is essentially, this is the I and J, or this is I and J. So then in this case, the probability would be Pi times Qj. And again, this is a joint distribution. It means that the sum of all the probabilities in this table would be equal to 1. And again, this is for 2 players. You can have it for, like, you can have a cube essentially for 3 players and so on. The sum over all cube would be equal. So there is landing probability. What is the probability that we are going in this cell? We can compute it because we can just multiply the probabilities. Then in this case, what is the, so for this guy, like the first guy, what is the payoff of these guys? The first player, say. Because here, as we had it, let me just use another one as well. Maybe this one. So here we have, for example, U1. Oh, it is not the best one. So here we have U1 and U2. So in each of these cells of this matrix, we have U1, U2. What is the utility of first person and what is the utility of the second player if they are taking this action and versus this action. So you need to compute, for example, for the first guy, you will compute Pj, Qj, and or P1, like Pj, Qj, and in this case, you should consider U1. And then you will sum it up. I will say actually better here. I don't say Ui, Uj, and you need to sum it up over all j's. That would be the expected probability for, this is player one actually, for player one. So this is the expected utility for player. It would be exactly the same for probability 2, except that instead of Uij of 1, you need to put it Uij of 2. The probability is still the same because they are landing at the same. This is the expected utility that we are talking about it. Again, consider the whole matrix, or like it can be even 2, 3, 4 dimensional. For each cell, you say what is the probability, landing probability, assuming these are independents, would be the multiplications of this probability. And then you will say that in this case, what is the payoff of this? This times that probability would be this. And again, the sum of the probabilities over the whole table is equal to 1. That's the meaning of expected utility. So that's the way essentially you can write it more formally. Is this one is essentially talking about the same thing. So expected utility is the sum over all action profiles of the profile's utility times this probability. So you can, I mean, we can write it this one. So essentially Ui of S is equal to over all actions that belongs to I, if this guy is taking this action, and you can say in terms of conditional probability, what is the probability of A conditioned on S? And S is a strategy profile. But if you want to see it essentially better, the way that I have mentioned is this one. So Ui of S1, S2, Sn, this is the strategy profile, is that you are taking essentially this one, A1, A2, An. So this actually belongs to An. So this is all action profiles. So for all action profiles, what's the meaning of all action profiles? It means that go to all cells of this matrix. So each action profile would be corresponding to one cell of the matrix, the payoff matrix. So instead that you will go to the all action profiles, so A or An, you can say this is the action profiles. You will go to all action profiles. So in this case, for this action profile, what is the utility of the ice player? Times the probability that we are landing here. What is the probability? This is exactly this one. This is the product of over all these strategies, all these mixed strategies, that each of them plays the corresponding action. So this is exactly, so this part is exactly this part, and then this part is this part that we talk. Good. Yeah.
Will we be given probabilities or
yes. Okay. So that's a good question. Are we given the probabilities? Whenever we talk about it, I mean, you need to compute, for example, these probabilities, or you are given these probabilities. But given the probabilities, then we can compute the exercise. So we need to know the probability. Either we need to compute it ourselves, or somebody has given to us. Either way, when we have the probabilities, when we have this matrix, then we can compute the expected utility of this class. So that's a very important one because we are working with it actually quite a lot, and we talk a lot in this game. Whenever it's a mixed strategy, we are talking about it. So later, we are talking more about these games essentially, and we talk about some kind of solution concepts. So what's the meaning of solution concepts? The whole idea is that like you have this matrix. So then the question is that what's the meaning of maximization, or what's the meaning of optimization in a game? So then as soon as you talk about optimization, I say, okay, you optimize for which player? Because you this is like 2 players. You cannot optimize for both, especially for zero-sum games. So it means that you want to optimize somehow for which player. And the issue, of course, it might be the case that for one player is very good, the other player is very bad. In that case, we will say that we are not in equilibrium. Because if you are playing in such a way that one person is in a very good situation, the other person is in a very bad situation, it means that in that case, the person who is in the bad situation changes his actions. They may go to the different. So in some sense, at the beginning, you may think about. So think for now about just pure strategies, but you can think about mixed strategies. Just makes it more complicated. But say I take some. We take some. But we have some action for player 1 and some action for player 2. They end up in some place in this table. So whenever they take essentially these actions, so these guys are taking some actions. So this action, I don't know, for example, we call it BI, and this is AJ. So whenever they take the action, we are coming someplace here. But the issue is that if the payoff in this case is not good for them, then one of them it might be not happy. So that person, maybe if this guy is not happy, then it changes to, I don't know, to something like BI prime. Then they are ending in another place in this table. And in this case, it might be the case that for AJ is not a good action. This person also now changes its actions to AJ prime. And so on and so forth. So in particular, I mean, they can essentially go round. Like essentially this one takes action, this takes action. The whole idea is the equilibrium is that we are reaching some place that both of them are somehow happy. And they don't want to change their actions if the other person does not want to change the action. This is a particular Nash equilibrium that we will talk more about. But now, this one that I mentioned about pure strategies, you can think about also mixed strategies. That now mixed strategies, I mean, they are not going just in one particular place. In some sense, when they are doing mixed strategies, they are all over the place. In that case, we talk about expected utility. We say that expected utility of this person is good or like is not enough. It may change it. What are the changes? It just changes the probability on different actions. Because that would be a different, essentially, a strategy. So it just changes the probability. So in some sense, you can say that when you change your pure strategy, also you are changing the probability distribution of that one, because you are essentially taking this pure strategy or action. You will put a probability 1 here. Now when you change it to another one, you take the probability 1 here and put all the probability on another action. So that's essentially the whole idea. We are considering some kinds of solution concepts that by some definitions both people are happy. That's the only way that we can do it. And that's the thing that happens in real world. As I mentioned, a good example of an equilibrium is a settlement. When the people go to the court, essentially, they settle. They settle means that something, okay, you don't get everything that you want generally. Otherwise, if you're not happy, probably you will go to the judge, that judge decides. But you say, okay, I don't get everything, you don't get everything, but most of us are happy with the current things. And the whole idea is that if you go to the judge, it might be worse for one of them. So it's okay, that might be, you don't know what is the probability. You may get better things, but who knows? You may actually lose a lot. So in some sense, equilibrium means settlement. We will talk more about it. And so let me go to the good. So we want to play a game. This is actually, we will talk the PBUT game, but just give some of the, summary of the past sessions that we talk about some basic concepts and basic tools, probability theory, as well as linear programming. And then we talk about, some motivations for the games, and in particular, some important class of problems like zero-sum games, non-zero-sum games, common payoff games, and symmetric games. And last but not least, we talk about utility. Utility means essentially the payoff if they are doing pure strategies. So payoff and utility would be used the same way, essentially. Then we have this concept of expected utility when we have randomizations or mixed strategies. And mixed strategies is just a probability distribution over the set of actions that a person can take. Good. Now, this is the game, actually, the very interesting and important game. I will talk more about it. It is called P-Beauty game. So I think the people at... let me say the game and then we will talk about it. So here, each person in the class or in some society or community, they are choose a number between 0 to 100. They will write on a piece of paper. They can write their name. You will fold the paper. And then you will give essentially this number. So who does win the game? The person wins the game who is, like, there are several rules, and these rules are super important. We can say that the person wins the game if he or she is closest to the average. That's one. The other one is that the person wins the game who is closest to the 2/3 of average. And another one we can think about that the person wins the game if that person is closest to the 3/2 of the average. And we will talk about it. This is actually a very important game. Again, this actually very interestingly describes a society or the community or the country that we live in. And I will talk about it. But let's play the game and then we will talk about it more in this session or the next session. Great. Okay, so we played this game, these two rules essentially, that who is putting essentially closest to average or like 3/2 the average. We could do it also 2/3 of average. And we got some numbers. The average for the first case was $45, when it was the average. And for the second case, it was 93. We will discuss more on these games. It is called P-Beauty game, and there's lots of nice things about it. That we will talk next. Okay. Bye.